on behalf of the Bangalore Chamber of Industry and Commerce, each one of you for this session on deep learning, computer vision, innovation, and digital technology. Before we could start the session, I will request a minute of a silence from all the participants that BCIC would like to offer its tribute to all those who have lost their lives to COVID-19 and pray for their soul rest in peace. And also, we like to express its gratitude to all the frontline COVID-19 warriors for their invaluable service. A minute of a silence from each one of you. Thank you all for the cooperation. Let's begin the session. This session has been organized under the aegis of Industry 4.0 Expert Committee of BCIC. We would like to especially thank Mr. N. Chandramouli, past President and Chairman of Industry 4.0 Expert Committee BCIC, and also like to specially thank Mr. T.R. Parshuram, our President and whole-time Director of Toyota Industries Engine Private Limited, and also Ms. Priya Ram, HR and Learning and Development at Drishti Technology, for facilitating this session for the benefit of our members. Drishti Technology is one of the very few Silicon Valley companies whose core R&D happens from India. Drishti works in leveraging AI by significantly improving production, manufacturing plant efficiency, by augmenting the capabilities of assembly line workers using deep learning, vision innovation developed in-house at Drishti. Drishti does not use off-the-shelf model downloaded from the internet. Instead, all the network models are invented at Drishti. 15 patent applications are in progress. And the person who oversees all and personally spearheads this effort is none other than today's speaker session, Dr. Krishnendra Chakraborty, who is the CTO and co-founder of Drishti. For the benefit of the participants, Krish is an ex-member of Google Research, Adobe Research, and ex-head of image science Flipkart. With dozens of patents in the area of computer vision and deep learning, he is considered as one of the world's top computer vision and deep learning expert. He is also the author of the book Math and Architecture of Deep Learning and has published many papers and in major journals and conferences of the world. Chris and his team has developed grounds up algorithms that enables action recognition with significantly improved accuracy in real time. They have also developed anomaly detection and improved action search engine working off the cloud, as well as set annotation tool that eliminated the limitation of single imaging annotation of the tools available at this time. On behalf of BCIC and our office bearers, we express our sincere thanks to Dr. Krish for accepting our invitation to address on this important subject. We would also like to thank all the participants for joining today's session. We request all the participants to kindly mute your webcam option and the mic, which will enhance and keep the bandwidth strong to avoid any disturbance. Please post your questions in the chat box only. The speaker will respond the questions during the session, or you could raise your hand. The speaker will be able to take it up. May I now invite our president, Mr. T.R. Parshuram, to welcome the gathering and take forward the session. Over to you, President, sir.
Thanks, Prithvi. Very good afternoon to all of you. On behalf of the Bangalore Chamber of Industry and Commerce, I extend a very, very hearty welcome to Dr. Krishnendra Chaudhary, a very senior person, the co-founder of Drishti Technologies in Silicon Valley. And we are very fortunate to get him today. He has a very wide experience and deep knowledge on the latest technologies, especially the machine learning, artificial intelligence, and its applications. So I'm also very happy to introduce my colleague, Mr. Chandramouli, who is the chairman of Mission 4.0, former president and also the former managing director of Making Starek. So welcome, Mr. Chandramouli.
Thank
And
you,
all
sir.
my colleagues for this very important session. I also thank Priya Ram for connecting us to organize this wonderful program. We are going to hear from a very great knowledge expert and a person who has been implementing several AI initiatives in the Silicon Valley, and he is spending a lot of time between India and Silicon Valley these days. So, Mr. Krishendu Chaudhary is a Chief Technical Officer and co-founder. He is an ex-member of Google Research Mountain View, Adobe Research San Jose, and ex-head Image Science Flipkart Bangalore, and author of the book Math and Architecture of Deep Learning, Manning Publications, New York, and he has a PhD from University of Kentucky. He has dozens of patents in the areas of computer vision and deep learning, artificial intelligence, and publications in major journals, conferences of the world. Krish is the world's foremost computer vision and deep learning expert. We are very, very happy to hear that. And mathematics for deep learning and Drishti technologies, Krish broadcast computer vision and deep learning expert. Here is a sample coverage you can go through. We can share the web access to all of you. And today, the whole world is undergoing a radical change in terms of transformation of new manufacturing. All these new technologies, the machine learning, artificial intelligence, big data, IoT, 3D printing, and all the blockchains, they're integrating to form a new set of manufacturing. And reflection of this COVID, we're going to see a new paradigm shift in the entire manufacturing arena. And work from home, even for manufacturing executives, then remote operations, unmanned operations, all these things are going to be the order of the day, whether we like it or not. Therefore, we have a very interesting expert on this. And I was very happy to see the other day the kind of innovations they have brought in. They are able to visualize most of the factories. In fact, one of the Toyota factory in West Virginia, I was seeing in one of their applications, you can see the entire factory running, whatever area you want to study, the cycle time, the movement of the operator, the movement of various pokayokes. From anywhere in the world, you can see it on a live platform. And they have been able to bring very powerful vision systems in manufacturing locations across the world. And their expertise is on integrating these platforms for a common purpose to maximize the manufacturing efficiency and also to remove the skill of the operator and also to improve the performance efficiency of manufacturing operations. So I don't want to take much of your time. And with this introduction, once again, I'm very thankful to Priya Ram, and once again, extend a very hearty welcome to Dr. Krish. Over to you, Mr. Krish. Thanks a lot. So
Dr. Krish, you have to unmute.
Krish, please unmute.
Am I audible now?
Yeah,
Very
perfect.
Perfect.
Yes. Thank you, Mr. Perceptron, Mr. Chandramouli et al. For inviting me here. And I wanted to thank Priya and Rupa for setting the whole thing up, and each one of you individually for attending this. This is indeed a great occasion to be together, and hopefully we will all have fun. So I am going to take the screen, share my. Is my screen visible? Can you see the first slide, for instance? Priya?
Krish, very well.
All right. Thanks a lot. So I don't want to talk more about myself. Mr. Perceptron has done a great job already. So I will directly take a deep dive into the main topic.
Sir, sorry to disturb you, sir.
Yeah.
Sir, we are able to see a different screen, sir, not the presentation slide.
Oh. One sec.
This is on math and architecture that you're sharing. Is that what you want to share, Krish?
No, I want to share the slide. Give me a moment.
Sure.
What do you see now? Do you see some diagrams?
Yeah, this is right.
Yes,
This is the perfect.
Perfect. Manufacturing, the eras.
That is correct. And you are seeing a full screen. You're seeing 3 diagrams. Is that
Yeah.
correct?
Yes,
Perfect,
you're right, sir.
perfect.
Full screen. Perfect.
Right. So, as we all know, manufacturing has gone through multiple eras. It has been around for over 100 years. And basically, manufacturing 1.0 was when the kind of started with James Watt's steam engine, when we started replacing muscle power with mechanization. The next era was electricity and mass production. And starting 1970s, kind of, we started having the computer era, where we started the first wave of computers, pretty much, which went on for 40 years or so. We replaced mindless, repetitive kind of manufacturing operations with automation. In some sense, we were actually making the work of the blue-collared workers easier. And then we are basically at the cusp of the next era, which we often call automation 4.0 or industry 4.0. It means a lot of things to a lot of people. I am going to mostly focus on the artificial intelligence aspect of it, mostly because that is what I know best. So how is this different from what we have been seeing? So we already have introduced computers in manufacturing quite a while ago, 30, 40 years ago. What is changing? I already kind of gave a little bit of a hint towards that when I said the original computation, the automation era, was replacing repetitive things where not too many decisions had to be made. So very mechanical types of works were going to be were handled by the machines. Now we are going to start the era where more cerebral, more front brain kind of work will be done by the by the computers. So this is the era of human-like decisions being made by AI systems. So let me quickly go over a bunch of business benefits that we can procure from the AI systems. This is not by no means a comprehensive list, but this would give you an idea, and I would develop upon 1 or 2 of these going forward. So it's important to kind of make the list right here. So one of the most important things that we can do via AI in manufacturing is predictive maintenance. What that means is the machine, the factory floor, the machine itself knows when it needs to go for repair. It would give a warning. Better still, it would directly call the maintenance person, maintenance department. It would send a message, but it can figure out. Remember, it's making decisions as to when it is its its useful life is nearing end, and it needs to undergo some sort of overhauling, oiling or whatever. It would know that directly, and that is roughly the meaning of predictive maintenance. This definitely is going to bring down downtime, and the benefits are very obvious. Another place where AI can really help, demand prediction. This is not specific to manufacturing. You can use demand prediction in retailing and other places. The rough idea is that you use inputs such as current prices, what was the sales history in the last 1 month or so, let's say, and you use all these inputs and you basically compute the predicted sales value for the next 1 week or 1 month or 2 days, whatever, but you are trying to predict how much demand is going to occur based on your sales history and such inputs. In fact, you can take the idea a little bit further. Remember, we are talking of Industry 4.0, where machines are talking to each other, they are all well connected, and we are trying to take the human out of the loop as much as possible. So, for instance, based on the demand, the warehouse can figure out when it's going to run low, and in an ideal science fiction scenario, it would actually start place an order to replenish. In the ideal scenario, it may even be talking to the trucks that are delivering the stuff to the warehouse. Is there a question? Okay, I'll go on. So, the trucks that are delivering the materials to the warehouse, they would communicate with the warehouse. Maybe the warehouse will fire its robots to prepare space for the incoming material and so forth. You can think of all sorts of AI-based scenarios, AI and IoT-based scenarios in this world. There is another area, and this in fact is closer to this, and the next one are the places where Drishti is, they're closer to Drishti and computer vision. There is the area, there is this thing called quality of product. You could install cameras on the factory floor and they would look at the product, checking for defects. For instance, if it's a automobile paint shop, you could look at the finished automobile and inspect for scratches, any kind of other marks, impressions, etc., any kind of deformity. And without a human inspecting, the machine basically determines if there is a defect and would raise alerts, and proper actions will be taken. And finally, there is the focus on people. Despite all the automation, a lot of manufacturing is still centered around people. This is exactly where Drishti would come in. I'll pick this thread up later, but right now I will just mention that despite all the automation, we are not able to take people out of the central loop. And people, basically, while people are the central strength, they also bring in their own weaknesses. They tire out, they make mistakes, etc. So if we have an intelligent decision-making system watching that and firing alarms such as a step was missed or something was done out of sequence, etc., then that would actually go a long way towards cutting down defective output. Similarly, people tire out. In fact, they're good on some days, they work very slowly on other days. Also, levels of trainings among people vary greatly from one place to another. If we could kind of generate productivity alerts and productivity statistics, that would go a long way towards. This is basically automated time and motion studies from video data. These are the focuses of Drishti. I'll come back to them later. But before we go deep into what Drishti does, let's take a step back. I am going to try and give you a high-level overview, like a redux of what this thing about which we all have heard, but many of us don't quite grasp the guts of this thing called deep learning or artificial intelligence. I am going to basically pretend that all of artificial intelligence is deep learning. There are other branches of machine learning. My personal belief is that they will wither in years to come. So we are only going to talk of neural networks, also known as deep learning. These are human-like decision-making systems. Let's see how they do that. Before I actually start giving you geometrical insights into that sort of thing, I want to point out something. All decision making ultimately can be represented, represented with mathematical functions. They will take in a set of inputs and they will output basically do this or basically a categorical variable, which is, let's take an example right here. Let's say, and this is a toy example, I have kept it deliberately simple. Let's say we are making a system which does the predictive maintenance. It would in real life take a large number of inputs, but for now let's pretend it takes only two types of inputs. It looks at the temperature and it watches the noise level. Basically, I am assuming when a machine starts going bad, it would make an odd noise. And let's pretend we have a system of we have a sensor which detects that noise, and we have a sensor which actually measures the temperature. And our simple toy-like system takes these two as input and outputs y. So the inputs of x0 is temperature and x1 is noise, and the output is basically the decision, maintenance needed or maintenance not needed. This is, we will kind of study this as a toy example to get insights into how these systems work. Of course, this is a toy example. Real life systems would have many more inputs and be in a higher dimensional space. But in this case, our input vector is two-dimensional, the dimensions being temperature and noise. So every input is a 2D point. Demand prediction is also another example here. This too is still a very simplistic example, but let's say we have 4 inputs. We will base our prediction of the demand on 4 variables: number of units sold last week, the price last week, are we offering discounts, because how much we will sell next week is very much dependent on discounts. One thing I learned in Flipkart. And also, how many days is Diwali? This is another thing we learned. Sales volumes pick up very seriously on the approach of a big event like Diwali or Christmas. So we put all these values as input, and we will get expected number of units sold as output. So here the input is a 4-dimensional vector. I have to point out at this point is that in real life systems, inputs are typically 100 or even thousands of dimensions. So we are talking of way more complex systems, but in order to get insights, we have to restrict ourselves to simplistic systems, which is what I'm going to do now. So basically, you can think of the input as a vector. For example, in the predictive maintenance system, the input vector is 2-dimensional. And I have graphically, pictorially depicted it. So most of this talk will be, I will focus on the geometry and pictures, and pretty much there is no math, but ultimately, if you really want to get insights into this, the math is kind of unavoidable after a certain point, but you can go quite a distance without actually going into the math. And this is the insight I'm trying to provide you. So consider this figure. It is a 2-dimensional plane. The x-axis corresponds to the temperature, one of our input dimensions. The y-axis corresponds to noise. And as we would expect, the larger, the more the temperature or noise, the likelihood of machine. Could somebody mute this? So the larger, the more the temperature, the further we go along the x-axis, or more the noise, that is further we go along y-axis, the larger is the likelihood of there being a their maintenance being needed. As a result, and if both of them, there is noise and the temperature is high, probably the machine is in a bad shape. So basically, as we go towards the top and the right, the likelihood of maintenance needed is higher, and towards the bottom and right, the higher the maintenance is needed zone is colored in red, maintenance not needed is colored in green. And I repeat that this is a very toy concocted example, so take this mostly as trying to get the idea across. So essentially, we have the whole input space divided into two zones. One is, yes, call the maintenance guy or call the maintenance department, which is red, and no, do not need to call the maintenance department, which is green. And they are separated by what is known as a decision boundary, which is the divider. The true decision boundary, as you will see, is this blue curved line. However, we often pretend that the decision boundary is a straight line or a plane in high dimension, and that approximate decision boundary is shown by this orange line here. So ultimately, it seems like almost too simple to be true, but this is true, that almost all of machine learning is identifying this decision boundary. And once we have identified the decision boundary, of course, we don't know what is the decision boundary for an arbitrary problem. But if somehow we can identify the decision boundary, then given a new input vector, all we have to see is which side of the decision boundary this is going to lie, our new income input vector lies. Based on that, we can output a decision, maintenance needed or not needed. So that brings us to the question of course, we don't know the decision boundary. How do we determine that? And remember, in reality, this is a very high dimensional space, and the decision boundary also will not be very simple straight line. It will be very complicated. The function, true function corresponding to the decision boundary is going to be absurdly complicated. Fortunately, we don't need to know that. All we need to know is a set of sample points on each partition. Remember, it's the same diagram, and we have the same decision, same two zones, excepting here what I'm trying to tell you with the dots is that we have only captured a few sample points on the red side, another few sample points on the green side. And that is all we need. This process is called training. We capture a few points, sample points. It's not always very few, in fact. It could be in the hundreds or even early thousands, but it's never going to be millions. Remember, there are millions and billions of points in the real space. The training data, these sample points are known as training data. On the training data, we typically need to know the output decision as well. And that training data is typically in thousands. So it's still many, many orders of magnitude less, but it's still an arduous task to create the training data. Today, we create it manually. That is to say, somebody would actually, some knowledgeable human would actually look at a lot of temperature and noise values and say, at this noise and value and temperature value, we do not, or we do need to call the maintenance department. This is how we manually create the training data. But remember, these are all only sample points. Now, one thing I would like you to note in these figures is the training data, while it can be sparse, we don't need to cover the space totally. However, it is kind of important for the training data to roughly represent the zones, kind of capture the outlines of the zones. It needs to be spread out enough to outline the zones. For example, look at the left side figure. You know, our training data is kind of low in volume, and if you look at the top left corner, there should have been red points there. Those red points are missing. And we have only a few samples in this red area, a few green samples here. Notice that as far as the training data is concerned, the orange line here would look like a good separator, good divider. It's dividing the training green points from the training red points very well. However, this is not going to do so great in practice when we let it out in the world on unforeseen points. Because if it gets a point here, I don't know if my mouse is visible, on the top left corner, which should have been classified as red, it will classify it as green, because our dividing surface, also known as the decision boundary, is not so neat in this case. If, on the other hand, our training data is a better set of samples, then the true orange divider, which we saw here, this orange divider, this is a pretty good approximator, although not the ideal one, which is the blue line. Still, the orange line is a pretty good differentiator. That would have been captured if the training data was reasonably a little bit more sparse, a little bit more spread out and more representative of the true zones that we are trying to separate here. So this is one lesson we get, which is so the two most important takeaways from this slide. One is we don't need to explicitly know the exact equation of the decision boundary. We can come up with a approximate decision boundary from a sampled set of points, which a sampled set of points on which we have manually curated and known the outputs. And the more representative the sample points are of the true zones, the better off we are, the less mistake we will make in creating the decision boundary. These are the two main takeaways I would like you to have from this slide. Of course, this can happen at higher dimension. Here we have tried to show 3D decision boundaries. So the points are in a three-dimensional space. Now, the divider or the classifier surface, or which is a plane again, is this blue plane. So the top left figure shows the training data sets, training sample points. Now, the top right, this is a bad decision boundary. As you can see, it's not separating the green and the red ones very cleanly, points very nicely. So it has basically a bad orientation. Similarly, it can be badly placed. Bottom left shows a decision boundary, a plain blue plane, which is wrongly positioned. Finally, the true decision boundary would look something like the bottom right corner shows, which very nicely separates the training data points between green and red sets. This is the fundamental idea of a classifier. In many senses, there is not much more. Of course, human brain cannot see anything beyond 3 dimensions, so I won't be able to show you figures of real life cases which are actually happening in hundreds or thousands of dimensional spaces. But the fundamental idea doesn't change, that I have training data points and I am trying to come up with a surface which cleanly separates, or as cleanly as possible. In many situations, we cannot fully distinguish, but we would try to do as good as we can kind of job there. So our decision boundary. And it need not be a plane in all cases. Only in simple, fortunate cases, we can get away with a planar decision boundary. In many cases, we cannot. Before we go there, I just want to kind of give you a two-dimensional sense of, remember this, this was basically our predictive maintenance zones, and we wanted to make a decision boundary between the green and the red one. And what so a classifier is essentially a function which outputs one value, let's call it 0, let's say, on the green side, another value, say 1, on the red side. In short, it's a step function like this. If we can rotate this three-dimensional figure on the right hand side such that this orange line aligns with this orange line, then the green part will fall on the green part and the red will fall on the red, and all points on the green side will have the value 0, all points on the red side will have the value 1. We have created a classical classifier function. So this is another big thing that is important to realize, is a classifier ultimately depends on a step function. So here is a simpler case, a two-dimensional classifier, but the idea is same. On one side we have 0, the other side we have 1. On the left we have 0, on the right we have 1. And of course, at higher dimensional, here is a three-dimensional classifier, we have already spoken about it. We can parameterize with W and B. The importance of the W and B, some of you would recognize that this is an equation of a plane on which we have superimposed the classifier, on which we have superimposed the step function. But let's not get into that sort of math. The intuition is, by altering the B, we could change the location of this step function. In other words, this step function could be moved left or right, or in this case, anywhere in the 3D space by changing the B, and the W kind of controls the orientation of the plane. This needs a little bit of more struggling, but still the main point is that we can orient and move around separated this classifier based on these are the parameters. W and B are the parameters that allow me to do that. And the whole thing, the whole function is known as a perceptron. This is basically the fundamental building block of a neural network. Think of a, remember, we are talking of absurdly complicated functions here. Nobody knows those. A, I don't know those functions, and B, even if I knew, if I have to find that function from scratch on every new problem that I encounter, there is no chance we will ever build a generic machine. So the great idea that neural networks bring in is basically we are creating those very complex decision boundaries by repeating a very simple function known as perceptron many times. It's kind of, think of perceptron as the brick. The whole neural network is like a house. I will place bricks in as many connections, and this is where so I connect these individual perceptrons in various fashion, and that is where the word network in neural networks comes in. A perceptron often is also known as a neuron because it is modeled after one neuron in human brain, and I can connect them together into what is known as a neural network. So one neuron is like one combination of one neuron in the brain. That is also known as a perceptron, and whole brain is like the house, whereas the neuron is like the brick. So by repeating and connecting them differently with each other, I can create as complex functions as I like. In fact, I made the point a little bit ago that not all decision boundaries are going to be easy and helpfully linear. Typical decision boundaries are absurdly crooked surfaces. How, in fact, let me show that even here, the real decision boundary was the blue curve, which was not straight line. For a while, we pretended with a single perceptron, I cannot mimic that blue curve. I have to approximate it with a single line. However, if I combine multiple perceptrons, I can actually mimic any arbitrary decision boundary. This is what I am trying to show here. Here is a fairly complicated curve. Now, by combining two perceptrons, each circle here, so basically a network of 3 perceptrons, I can create what is known as a tower structure. And this is the insight into something which is called Cybenkos Theorem. The idea is that the tower structure, we can repeat it, and remember, I can adjust the height of the tower as well as the location of the tower. By putting very large number of towers like this, as shown in the right hand side, I can identify any arbitrary function, which ultimately translates to I can combine neurons or perceptrons and essentially mimic any decision boundary. This is the fundamental idea behind neural networks. We can, in theory, remember there is a trick here. I am not saying how many perceptrons will be needed. In many cases, the number of perceptrons needed may be prohibitively large. So we really won't be able to do it with finite hardware resources we have. But in theory, if I am allowed to connect as many neurons as I need, I should be able to mimic any decision in the world, which is to say any complex decision boundary can be mimicked with perceptrons, which is roughly the idea being expressed in this slide. Now, I will, so basically, this is the core idea. I have tried to reduce pretty much what sometimes takes some people a lifetime of reading into 15-20 minute detour. So obviously, it won't be totally apparent, but I can stop now and take questions, or we can do that afterwards, because I'm going to shift gear a little bit and move into what is being done into Drishti in the rest of the talk. Okay, I will move forward and hopefully there will be questions at the end. So now that we have seen, we have gotten at least a high-level glimpse of neural networks, let us now come back to the question of manufacturing, what AI can do in manufacturing. In particular, what are we all about at Drishti? So this is basically a repeat of the diagram I showed at the beginning of this presentation, where I have shown the three eras of manufacturing. What is the common thing we see in all of these? So the era one used steam engine, then came electricity, then came low-level automation. But what is constantly there? That's right. Every single one needs human beings. As I mentioned at the beginning of this talk, no matter what we do, we cannot take human beings out of the equation in manufacturing. We are very, very far away from that. We have reduced the number of human beings. We have reduced the amount of muscle necessary from these human beings. And now we are kind of double checking the decisions made by those human beings, but the human being is not going to go away.
On the lighter side, Krish,
yeah,
Chandramouli here.
Yes.
To go back to the picture, the third person is wearing more cleaner dress than the previous other two. Okay.
Absolutely.
Great. I'm enjoying the session now. Please carry on. Sorry.
I agree with that. Good.
More than 150 people have joined and they are listening to you. More and more people are joining as we are talking.
Thank you.
Fantastic. Thank you, sir. Please proceed.
So, I don't know. This is the top. The headline is actually a quote from many years ago. I suspect most people in Bangalore in the audience are too young to remember this. This is a quote from the Clinton election. Bill Clinton got elected, and I was kind of new in United States. In those days, I was impressed by his election campaign ran. They had this huge printout on the back of their election campaign. It's the economy, stupid. Basically, they tried to say that nothing else matters. This election will be won or lost on the economy. That was true of the Clinton election. Their opponents focused on many other things, but Bill Clinton focused on only the economy and won. I tried to make a lame attempt towards the joke around that. I tried to say it's the people's debate. Ultimately, what I mean here is the whole, we unless we study people and cover up for their weaknesses, we are not going to have a really efficient and error-free, high-quality, high-productivity manufacturing, basically. Because first of all, people are not going to completely go away. Manufacturing depends on their innovation, their thinking power, their ability to deal with unplanned situations. But at the same time, people, unlike machines, they make mistakes, they get tired, they perform good on some days, don't perform so good on some other days. And that is Drishti tries to smooth things out. How am I doing on time? Anybody, Priya, do you know how much time I have left?
Sir, no problem. Please proceed, sir.
Okay, I would like to try to keep this less than an hour, so let me just go through a little bit faster. So basically, Drishti chose to focus on people. This is a little bit of a irony. We are an cutting edge industry 4.0 company which is putting its money on people. This is very weird, but basically we are trying to make humans competitive in an increasingly automated world. This is what Drishti does. We will see how in a second. Basically, we focus on quality and productivity. How so quality? Quality basically means, first of all, if the human being did miss a step, basically Drishti install cameras on the factory floor. These cameras capture what is happening in the video, and the video is transmitted to the backend where our deep learning engine sits. And we have spoken quite a bit about deep learning so far, although that is kind of toy compared to what we really do. But essentially at the backend, we have our deep learning engine, which analyzes the video. What it does is, specifically, it does two things. First, it does cycle detection. As we all know, manufacturing is a repetitive thing. Units enter the workstation, get worked upon, and then they leave. This is one cycle. So Drishti identifies every cycle on the manufacturing floor for as long as the camera is on. Drishti also does action detection. As Drishti does action detection, these two together allows Drishti to do the following. First, every time if the worker misses an action, we could emit a near real-time warning. It's not perfectly real-time, to be honest, but it's close enough for all practical purposes. So we will emit a real-time warning. Similarly, we could emit a warning when there was an out of sequence. Let's say the factory has determined that the most efficient way of doing these operations is A, B, action A followed by action B followed by action C. And then some operator does action A, C, and B. We would be able to emit a warning saying, no, you didn't do the right, didn't do them in the right order. You have to switch and do A, B, C. So that's one thing. This is how we help quality. There is also productivity angle, which is, remember, we are measuring the start and end point of every cycle and every action, which means we will be able to generate analytics data on those action completion time. Overall, this is the time and motion study I referred to at the beginning of the talk, which basically we can say that, first of all, we can identify the bottleneck station. We can identify the bottleneck station, and so that we can even identify bottleneck actions, the action which is slowing down that station, or the action which is slowing down every other action, basically causing others to wait. We can identify that bottleneck. We can also kind of get the big picture sense of what is slowing things down. Answer questions like, say, what makes the Bangalore factory much smarter than the one in Timbuktu? Of course, Bangalore has to be the fastest factory in this talk, right? So essentially, we are able to get insights like that. Or I have 3 shifts. Let's say there are 3 shifts, and we discovered that the cycle lengths are longest typically during the afternoon shift in a Calcutta factory. And maybe they will decide to stop serving rice during the lunch. That's sort of, I mean, I made a little bit of a joke, and but the point is, you can investigate what is causing loss of productivity. Now, so we do cycle detection and action detection. There is one important point. Let me, so in cycle detection, we are using fairly deep innovative, in both of them we have fairly deeply innovative, and as Mr. Parsonam mentioned at the beginning of this talk, that we do not use off-the-shelf neural networks downloaded from the internet. These are all invented at Drishti. Patents have been applied for, granted in 1 or 2 cases, and these are best in class in the entire planet. As far as published stuff goes, I am not aware of anybody doing better than us in these problems. There has been a few tests run by our clients. We are the most accurate. We are not the fastest, unfortunately, but we are the most accurate. What gives us this accuracy? So there are 2 things that I have highlighted here. One is the AVAE, the other is the 3D convolution. I will talk about the 3D convolution first. First of all, it's easier to understand, and also it's about accuracy. Essentially, let me give you an idea of this. So if I am, let's say I am capturing a video of a door closing or opening. If I show you a single frame of that video, you will see the door halfway in between closed and open. Would you be able to tell me whether the door is opening or closing just from that one single frame? You can't, because you can't see which direction it's moving. In other words, there is not enough information. No matter of smartness in the neural network would give me the full info, give me the total info that is there in the 3 dimension. Here the 3D means actually length, breadth, and time. The 3rd dimension is not z height, it's time here. So the 3rd dimension, namely time, the entire video has information that is just, if I do things one video frame at a time, there is no way I can be as accurate, because I'm basically chopping off an important source of information which is temporal. As a result, we do 3D convolution. When we started in 2018, this was very novel. Now, there you will start seeing other, at least academia, industry is catching up with 3D convolution. Industry is still kind of rare, but you will start, good papers are coming out with 3D convolution these days. We are becoming less, but still we are one of the foremost in the world, but we are not totally unique as we used to do in 3D convolution now. However, we do have another invention which is still unmatched in the world, which is, remember when I was explaining deep learning, I said that we have to create training data manually, which means we have to take a set of sample inputs and manually label them with the correct output, the known correct output, which is also sometimes called ground truth. Now, one of our inventions is to have a system where this need for manual curation is drastically reduced. As a result, we will give very few examples, and we will be able to train a neural network from those very short number of examples. this becomes important in situations like defect inspection. If we go to a company like Toyota, they have like what, 6 parts per million defect, maybe even less. Maybe I'm angering Mr. Parasuram with 6 parts per million. But anyway, it's a minuscule.
Yeah, I think there are some variations. Yes, you're absolutely right. Most of the plants have less than 6 ppm.
Thank you. So it's very hard to create training examples for the defects. They happen so rarely. And that is where this technology could come in handful. We are also using it in our people because cutting down the amount of manual training data also brings down the cost of the system, because human beings are expensive, and we can come up very fast. But that is what is our almost unsupervised anchored variational autoencoders. So, and I have already spoken about the second point, the 3D convolution. Let us now talk about, this is the fun part. I will show some example videos. Let me know if they're visible clearly. I can't see the other end, right? So, I will stop and just give you a sense of first what to expect here. Basically, this is a car radiator manufacturing factory. You will see a car radiator coming in. That's called the unit. And this is a real example from a real life client. We have not shown the client's name for privacy, but this is a real life example and output of our system, not a concocted video that I have created just for demoing in this talk. You will see the neural network on the fly captures when the cycle starts. You will see a green rectangle, which is basically the bounding box of the region of interest, basically where action is happening. And you will see the green rectangle. At the bottom of the green rectangle, what is happening as found by the neural network will be labeled. And remember, you will see somewhat inscrutable names. To the mechanical engineers and industrial engineers, these names might make sense. To computer scientists, they won't make sense. But these are the names which we got from the clients, and these are the names with which they call these actions. So the recognized action will be labeled at the bottom. They will also appear on the side. This is the complete set of actions as from the previous cycle. A new cycle is now going to begin. You will see the right hand panel clear, and then as and when actions occur, you will see them populated on the right hand side, and also you'll see them labeled at the bottom of the green rectangle. I will try to stay quiet mostly because the video is self-explanatory. Keep reading whatever seems to be appearing in green, keep reading those. So cycle start. Place jig right, place jig left. Install packing right, align wires. Then install packing left, press packing left, then obtain marker, and cycle finished. This cycle took 36.17 seconds. So this is roughly what Drishti does. You will know, you have seen both the cycle and the action detection real demo, and kind of now it should start falling in place. From this we actually know the duration of the cycle. As you saw, it was what, 46.17 second, and then we didn't show them, but we know the duration of every action because we knew the start point and the end point of every action, and we have a website where we would publish analytics, website where the client can log in and see the analytics on these completion times, from which they can derive insights as to what is the bottleneck station, where is the what is causing the slowness. They can even do search and say, okay, show me some of the longest cycles. I want to know what is causing the cycles to become long, and they can look at that. And they can, of course, check for missed actions. Here is an actual demo for missed actions. Um, So again, let me give a quick running commentary. So you will see two cycles here. The first cycle is fine. It's there for context. And you will see engine coming in and getting walked upon and then leaving. We are capturing the actions. And then there will be another cycle for some reason on which no work is performed, and we will generate red lettered warnings to outline that. So they're doing Titan fuel pipe bottom, and then this unit is going to leave. The next unit is coming in. The previous cycle was completed. A new cycle just started. With the unit is kind of coming in. Now watch the left unit. You will see that no action is being performed on this left unit. And the system has understood that none of these actions were performed. It has created a red letter set of warnings saying missed actions on this set, which is another of the Drishti value propositions. So that gives you a nutshell idea of what Drishti is all about. There are huge things that I have not covered. Uh, for various reasons, from IP protection to various other things, meaning we have to be tread carefully on that. The point is, we have a huge infrastructure developed, a whole infrastructure developed for the video flow pipeline, for the databases. All this is staying in the database, and we can search later for every single cycle, and the video and the annotations will come up as a result of the search. So all this is there, and there is a fairly complex pipeline. In fact, at this point, we are putting probably more, probably we are putting more engineers on the infrastructure compared to the neural networks at the moment. But we started with the hardest problem, which was the neural network unsolved problem, and now we are setting up the whole infrastructure, and the whole thing works on a client side. This brings me to the last slide, and about time I am beginning to lose energy. So basically, I'll just recap what I have said. So Drishti mostly does productivity and quality. We install video cameras on the factory floor, which the videos come to the backend where our deep learning engine sits and analyzes the video. The core technology comprises of cycle detector, action detector, video flow pipeline, storage, and video snippet search. where we have significant innovations, which I did not get, I haven't discussed here, and that is more for a deeper tech kind of talks. So the business values we are talking about, again, we have discussed most of them. We are giving quality warnings near real time, missed step and out of sequence. We have done product, we can give productivity insights, such as what is the efficiency bottleneck. We can view anomalous cycles, very long or very short, and see what went wrong in those cycles and get some insights into what is ailing the factory floor, for instance. Then we can use some of the very good videos for training. This is one thing I haven't mentioned so far. Look, as I said, human beings need to learn, right? So if we find a particular good worker, we may have worker churn, and that guy or girl might leave tomorrow. But we can use the video. We will be able to capture some of the best timings automatically and show them to new joinees as training videos. And this can be made arbitrarily more complex, although we don't have direct products for that. But we can even capture the new joinee and time that person and say you are still not as good as the other person. You're 20% below that, 10% below, and at some point declare victory. We can do all this, and of course we do store video records, which is, as we know, a picture is worth 1,000 words. Video is probably worth 10,000 words. So we are storing everything that happens. In fact, there has been cases where our clients, where let's say we have a client who is a vendor of another company, and they get unfairly accused of some quality problem. They can actually go back to their video and show them, look, that here is the video of that piece being manufactured. It wasn't us who inserted that defect. Things like that are also possible. So I will stop at this point, and I will also stop sharing. And I will be happy to take questions at this point. And so the main screen is back, right? I can see Mr. Person.
Yeah, I think thank you, sir. Wonderful. Really brought the beautiful insight of neural networks and back to basics of machine learning and artificial intelligence. Of course, to some of us, it was a bit easy to MC scare when you talked about the equations. Maybe we'll have to get back to our college days and we'll have to refresh. But I think the big picture what you brought was something phenomenal. I think how we built element by element, and the good zone and the bad zone, and the door opening is a very classic example. When a door is halfway opened, I think how to detect it's going to close or open. I think you put it very, very nicely. Most of us have been always talking about how to replicate brain. Of course, it's all our imaginations. But I was in a global conference at Kyoto, where I could meet a lot of Nobel laureates. One of the sessions was on, brain mapping and how to create a human brain. That was a kind of a discussion among the Nobel laureates and a lot of experts on machine learning, artificial intelligence. And finally, at the end of the session, they concluded that probably they could not even approach 1% of the brain's reproducibility. I think that is a fact of matter. So, in fact, when you talk today about creating the good points and the bad points, and how to induce machine learning process step by step, teach the machine, I think this is an amazing concept. And some of the practical applications, what you showed through Drishti is amazing. In fact, most of the automobile applications or manufacturing applications, today the biggest challenge is human errors. I think how to avoid human errors. Same time, human in manufacturing is impossible to replace, as you rightly said. Therefore, how to avoid the errors in human beings? I think that's where the whole crux of the problem lies. And I think definitely going way forward, we see that these kind of technologies are going to rule the world with a lesser and lesser number of people. So when I visited one of the plants in Japan, I was amazed to see the Sony factory, only 2 people, 1 dog and a human being. The purpose of the dog was to ensure that nobody enters, and the person's job was to feed the dog. So this is long time back. So the automated factories are going to increase as the days pass by. And the people dependency also is going to be there. We cannot remove people. So I could see 2 things. One is the predictive maintenance, the preventive maintenance, and the mission factors, even in an unmanned situation, where manned situation which is going to exist for next few decades in several developing economies. I'm able to see a huge application of these kind of software to detect the movements of people, error making, and also to prove to the customer that, hey, what you did is right. Here is the video. And element by element, the tracking of the cycle times and the motions, which will help us to standardize these manufacturing processes for a period of time and create a kind of a good zone and NG zone. So we are really, really thankful to you. And Mr. Chandramouli would take you through the Q&A session. It's over to Mr. Mouli.
Mr. Mouli?
Mr. Chandramouli? I think there's a problem from his network.
I think, President sir, I think Prakash sir can lead.
Yeah, Prakash is the chair of our manufacturing committee. Again, he is from Toyota plant, Toyota Kirloskar Auto Parts. He has worked in Toyota Motor Japan. I think for a couple of years he worked in the automotive. Yeah. I think we are missing you.
So there is a small internet blip. I mean, Prakash can handle, no issue. I have a personal question myself. So I will start with one question and then Prakash can alternate.
Interact now with some.
Then we will get an interactive kind of. Am I audible? Am I audible?
Yes, sir. You're audible, sir. Please go ahead, sir.
Yeah, I think Rupa has.
There's a problem. We're not able to hear you.
Hello, am I audible, Mr. Krish?
You're audible, sir. Please go ahead, sir.
I can hear you, Mr. Parsunam, Chandramouli.
Yeah. So I think I'm able to ask one question.
Sir,
yeah, Prakash can come in, but before
so
that.
You're able to hear Mr. Krish, what Chandramouli is telling?
Yes, I can hear him.
Yes. Okay. Parasuram has given me an unenabled task of handling the Q&A. Thank you, Mr. Parasuram. First of all, at the outset, I would like to thank Mr. Krish to explain in such a rudimentary fashion the meaning of artificial intelligence and deep learning. And for the first time, I understood the topic. So thank you very much from my personal side. And coming to the vision technology is, of course, is a huge area. And I can ask you a question for the benefit of the audience.
Yes.
India has got many labor-intensive assembly sectors. See, the capital-intensive sectors, we are very familiar, as automobile, Toyota and other projects. But there are many labor-intensive assembly sectors, Mr. Krish, Dr. Krish. And here again, the dull and dirty and dangerous and diabolic kind of actions are there. And people are trying to automate these areas. But there are many areas like the shoe manufacturing, like the textile garment manufacturing, is got so much of dexterity involved.
Yes.
The replacement of human being is unthinkable even in the Western world, which is why they moved away to India, China, Indonesia, Bangladesh, Sri Lanka for making garments and shoes, except the sports shoes, which are sometimes plastic and things like that. So in this area, I was talking to Ramana the other day, COO. There could be a huge potential in India. What is your take on this? That even looking at the multiple motion study and improving the productivity as well as the quality, the missed actions are many in those sectors. If I miss one stitch, you can imagine what happens to the shirt. Or if I miss one button, you can see that shirt, a $200 shirt will be worth only $10 in the platforms of India. So on behalf of such labor-intensive market in India, Bangladesh, etc., I want to raise this point. Can we use Drishti technologies? Over to you, sir.
Yeah, thanks. That's a great question. So the first Uber answer is yes, one word answer. We should be able to use. Look, a lot of this is sensitive to the camera placement. It is something I did not quite outline in the talk. The more intricate the action we need to capture, the closer the camera has to be. In factories, most of the time, we are trying to capture kind of crude actions. Did that person really put hand inside that thing, or was that pushed out? That sort of thing. That is why the cameras are kind of far away. That's the demos I showed. But as Ramana must have pointed out to you, if we place the cameras closer enough, there is nothing in theory that stops us from capturing, picking up on smaller actions. Of course, the camera has to have a clean view of what is aimed at capturing. That is not as easy as it sounds. Quite often what happens is the human being actually covers the camera view with his or her head or back of the palm and so forth. Those things are the caveats. But that being said, there is nothing fundamentally that stops us from applying this technology. In fact, that is an exciting prospect. We love to do that. I am not fully the right person to talk about if this is business-wise feasible. Like, is it dollar-wise the right direction to go? You should talk to Ravana and more and Prasad, etc.
I'm talking from technical side, from the technical point of view.
Technical side, the answer is yes.
Not the business feasibility, but technical feasibility.
Absolutely, which is what I'm doing. From the technical side,
which is why I'm asking you instead of Ravana.
Yes, I don't even know if he's online or not.
No, it's okay. I can ask him also.
Yeah,
online.
Okay, great. Ramana, you might want to pitch in there. I will just talk from the technical end.
Technical end. Yeah.
So technically, there is nothing that stops us if you give us a good camera placement. That is, with the proper camera placement, these are, there are, if you go to extreme details, there are issues such as, very intricate finger motions. Right now, the technology we have is kind of geared towards capturing big motions.
Oh, I see. Okay, got it.
Big motions. So, did you do this? That is going to be a little bit harder, but that is not a theoretical limitation. It's just something. If there is enough business case, we can go ahead and build that sort of model also.
Understand.
Right now, though, we are more geared toward big actions. Can you see my hands?
Tightening.
But
tightening the bolts, etc.
Minor twists of fingers, etc. We are not very well geared to capture at the moment. This is not an inherent limitation, just the way we have decided to go business-wise. So, Ramana, if you're online, you may want to comment on the the economic, financial feasibility of these things.
Rupa, you need
right
to
now I'm
unmute
asking only the.
So
right now I'm asking only the technical feasibility.
Got you. Okay.
But Dr. Ramana can throw some light on how to bring it to the developing country. You see, automobile industry and aeronautical industry, there is an operation called riveting. There are millions of rivets on every fuselage, and it is still even now being done by several human beings, which is why even the best of the aircrafts, when they are assembled in India, they come for a low-cost trade-off, and therefore I've seen factories in Hyderabad and other places where Tata and other companies are building it for Switzerland with manual riveting, but there is a gun, of course, but there are several hundreds of rivets. So
if you missed one, that is what we can capture.
Exactly. Yeah, here the quality issue is missing one. Productivity issue is what is the cycle time of putting all those rivets in place.
Yes.
And because this, every pin has to be inserted and all. So I could, on the one hand, of the extreme level of leather garments and textile garments at this end of the spectrum, to the other end of the spectrum, like aeronautical fuselage, that could be many labor-intensive operation. I just want to throw some light on that. But anyway, I think I got your answer that larger motions, such as automobile, tightening of an engine, etc., captured. On that note, in your slide, sir, you did not show the video without drishti. There was on video.
Yes.
For some reason, you did not show that. For a reason, I think.
In the interest of time, but
okay. Because when you compare with and without, the audience, it is, my friend Prakash is going to ask a question now. He is a friend of Kaizen philosophy. Unless we see before and after, the human mind doesn't understand the benefit of it.
That is exactly what we use for Kaizen. I thought I keep it with in time, and if there is interest, I can go back.
I thought only I missed it because of the internet problem in my computer.
No. I skipped over it because I was trying hard to exactly. It would be without those green rectangles, the same video.
Okay. So, same video without those data.
Same video without the green rectangles. And yes, that is exactly Kaizen. That is an exciting comment that you make. We deal with it every Kaizen. So thank you, and very, very minutely perceptive of you.
I'm looking for questions in the text box. While there are 150 people plus keep on joining, Mr. Prithvi can help me. Rupa can help me. I could see some questions, and then if there are not many interesting questions, I will ask Prakash ji to put some question. But there is one question from Mr. Jagdish Kumar. I think he's from RBI, Reserve Bank of India, maybe.
No, it's part of Bosch, sir.
Oh, okay. Robert Bosch, sorry.
Yes.
Robert Bosch of India. He's also RBI. Very good.
Yeah.
Okay. He's asking, is it possible to analyze the skill of operator and identify improvement opportunities using this technology? That seems to be the fundamental question. Go ahead, sir.
So basically, by the way, I see a lot of messages on the side saying that we lost access to the chat now. Anyway, I will not go deep into that.
No, that is a technology problem.
Okay.
But at least it's an interesting point. Yeah, majority of them saying they are not able to chat. Okay.
Right.
But,
okay.
So that is a technology issue.
Can't fix it right now. Is it possible to analyze the skill of operator and identify? Yeah, absolutely. I actually referred to that. That is one of the great usages of this technology, that we can measure the timing and come back with suggestions for improvement and also create training. We can even capture the really fast operators video and use it to train, and also tell the operator where exactly this operator is slowing down and what needs improvement and where the operator is doing great, and all these analytics can be provided through the technology.
Okay.
Mr. Jagdish Kumar, does that answer your question?
Yes.
Not sure whether it's there.
Clear,
he's there.
Yeah.
Thank you, Mr. Jagdish Kumar.
Yeah,
now, I think, Rupa, there must be a problem. There are a set of participants, 11 participants, which are like a co-host, like me and Parsuram, and there are hundreds of people who are not participants. Maybe there is a technology issue. Sorry, apologies for all the audience who are unable to text the messages. But Prakash ji, go ahead, sir. Mr. Prakash, go ahead.
Maybe one last question, Prakash. Maybe one last
Prakash is
question
asking
today.
Right. It's not your question, Mr. Prakash. Do you want to read it out?
Sorry, I think because of the time, maybe I've just put it in the chat box. I have 3 questions actually. This we have gone through, and I mean, first of all, thank you very much, because we were just looking for such a solution about a year back or 1.5 years back. But I think today it is wonderful to hear from you about this kind of a solution exists. I have one question related to how is this, because we are also searching for such tool. We have come across Intense Eye. I think you would have heard of this intenseye.com.
Yes.
How is that? I mean, how is your solution different from that? Second question is also Microsoft has been developing HoloLens, probably. So probably that is also trying to do the similar thing, but maybe you can elaborate on that a little bit, how it is different. And can you integrate this software to a normal CCTV camera? These are 3 questions from my side.
I will tackle them one at a time. So so the solution really, the difference really lies in the how. We are actually, we believe, way significantly more accurate because of the way we solve the problem. So the difference lies in the method. So I believe HoloLens, for instance, was tried by Toyota and was found to be unsatisfactory in quality. So given that, uh, I may be wrong about that. This is roughly what I'm recollecting. Our So the main difference lies, we are like I said, we are not using off-the-shelf tools like they do to solve. They have a solution which is largely based on, they are mostly tracking the hand motion. We, on the other hand, are looking at a more complex ensemble of the hand. They are basically going with, specifically they're detecting points on the hand and tracking how they're moving, which is a good way to go, excepting what tool is being held. If somebody is doing with a screwdriver versus something else, that also is a cue. Neglecting that cue leads to loss of accuracy. And similarly, what is the object on which action is being performed, that is also a cue. So uh, all these cues are used by our method, whereas that does make us our onboarding time go longer, but it's definitely accurate. This is the direction we're taking. Similarly, we probably will work on CCTV. This, I am not answering this from actually having tried out and seen, but from, there is nothing in theory that stops us from being functional on CCTV camera. We don't need that much of a high resolution. CCTV camera is low resolution. We will in all likelihood work. However, I am not talking from actually having experimental verification of that. That what I said is mostly a theoretical guess. There is no reason why we wouldn't work on CCTV video. So, however,
Please go ahead, sir.
Sorry, what I was saying is, in factories, really the extra $200, so what a camera costs, like what, in $100 range, that is nothing to a factory like Toyota. So we did not try to save that cost for them. And
my question was not from that angle. Generally, what happens, you have too many cameras also, it creates a lot of conflict. So from that angle, I asked, if whatever cameras we have, if those cameras are powerful enough to focus and do that, and we can integrate this solution, it will definitely help. So from that angle, I asked.
I agree with that, but also remember, we need a specific, if the CCTV, it's not the resolution of the CCTV camera that will stop us, but it's possible that the CCTV camera is placed at the very high ceiling from which the camera may not be able to see the screwdriver or
Okay.
action.
Understood.
If
Thank
that,
you. I think I understood your point. Thank you very much for the answer.
Dr. Krish, can we wind up with this?
No, Prakash's third question is very important. If it is okay with Dr. Krish, is integrating augmented reality. The HoloLens became popular in the augmented reality, and they have done the tie-up with Rockwell and PTC. So Microsoft Rockwell PTC is a kind of alliance. With that and the vision technology, for example, assembly line training, service training, remote maintenance training, is that an area where there are some applications happening by Drishti? Combining augmented reality and vision technology?
Right now, it's not happening.
Okay.
Once this can be done very easily. We did a bit of a towards the beginning, where we got the feedback from the industry that augmented reality, at least in the Western world, is not something that the workers are liking very much in training. I don't know if it has changed. I'm talking of 2 years ago. At that point, what I heard is, so we went to one of the factories that we surveyed. They said that after half an hour, everybody took off their glasses because it was giving them headaches.
Yeah. But now it has come. Now it has come on handheld devices. In the tablets and this one, when the AR is functioning without the wearable but on the handheld devices, it has caught up again and it become popular even in India.
In that, we probably want to look at it again. We basically did not pursue that angle based on the feedback in 2018.
I agree with you about this. Yeah, it's too heavy, and even one place I tried it, it's too cumbersome. It's too heavy and.
And one thing we tried very heavily hard is not to fall foul of the unions. Meaning, if it kind of gets branded as workers are hating this because there is a heavy glass or it's
Absolutely.
we have no chance. So we totally anything that disturbs the worker, we are not going to do that. That was roughly the direction taken. So yeah, which is kind of.
Okay, I think one last question has come. I don't know, for want of time, should we close it or we should just respect that one last question from Mr. Borkar. Please elaborate on the methods to detect and eradicate the caveats which are caused during camera capture of the labor's position with respect to camera. So it's a very technical, micro level question.
I know what is the so. Essentially, and this is what you are asking, Mr. Borkar, is something that is essential in Europe because of GDPR. In Europe, they have very high privacy standards, much higher than USA, in fact, and there we do this. Detecting a human head with our technology is trivial. We actually have a head detector. However, what we have really done is these days many cameras come with face and head detectors, so that is even a higher level of privacy, and that is what we employ. The camera itself blurs the head when it, so the video with PII doesn't even reach drishti. When it comes to drishti, it's already the human being is blurred out, the head is blurred out, head and face. That is roughly what this is how we solve the problem. Although our software is perfectly capable of detecting the head and blurring it out as well, but then it's slightly lower degree of privacy because it has already reached drishti when it's being blurred out. Deleting it in the camera itself, then nobody is seeing the that is like max privacy, which is what we do.
Thank you, sir. I think Mr. Parasuram, sir, would you like to place the closing remarks, Mr. Parasuram? Maybe he's not in the session now. Okay, on his behalf and on behalf of BCIC, I really thank Dr. Krish, Ms. Priyaram and Ramana. We have been looking forward to this session for the last couple of months, and it has happened finally. And the well-timed, I would say, because now the workers have started going back to the factory after the second wave of COVID. So I think the timing also was very optimum. And Mr. Prakash, who's the head of our manufacturing committee, is planning to do a large conference in the month of September or so. And he will again get in touch with Priya Ram for engaging your experts to educate us on the area of neural network on the one hand and vision technology on the other hand. But I like the way you started your very first slide. What are the business value propositions? And then you went on with it. In fact, most of the time in the webinars, they start with the technology and end with the value proposition. By the time people have lost the interest. You did the other way around. Great show, Dr. Krish. And you also ended it with that same thing at the end. You started business value, you ended with business value. In between, only thing which I personally could not understand is the two silos of neural network and vision technology, the connectivity. Maybe another session we will discuss that.
Another too small.
Correct, because you had it as deliberately, you had it you created a curiosity for another session.
Yes.
On that note, thank you very much, Dr. Krish and Prakash and Mr. Parasuram, if he is still on the line. And thank all the organizers. So Parasuram sir, some closing remark I made, and you want to add something?
No. I think he literally brought the summary first. I think that's the global way.
Thank you.
Right. Also, we summarize.
Summarize in one page, but nowadays it has become. Thank you, sir.
But
and
today
I think,
was a wonderful session. Eye-opener for many of us.
Eye-opener.
And definitely, we would like to collaborate and learn more from you the days to come. And we have a manufacturing committee. Mr. Chandramouli is heading the Mission 4.0. Mr. Prakash is heading the manufacturing committee, and we have a MSME council headed by the Volvo head, Mr. Indu Shekhar. So we are all a lot of manufacturing companies. I'm sure we will have this presentation in our website so that a lot of companies would be interested. So we look forward, and once again, thank you very much for sparing a valuable time, for bringing a very bird's eye view of the neural network and the AI applications, and of course some of the examples of Drishti. So really appreciate, and a token of our appreciation, I hand it over to Mr. Prithvi for felicitation.
Yeah, thank you, President sir. Dr. Krish, as a token of appreciation from the chamber and from the office bearers, we would like to give you a virtual memento, and we will ensure that it reaches your home or your office. And then after this, we'll have our national anthem played before we conclude.
Prithvi, the national anthem is coming?
Yeah,
or you expect all, I thought you wanted all the 150 to stand up.
No, 1 minute.
Okay.
A minute, sir.
जनगण मन अधिनायक जय हे भारत भाग्य विधाता पंजाब सिंध गुजरात मराठा द्राविड उत्कल बंगा विंध्य हिमाचल यमुना गंगा उच्चल जलधि तरंगा तव शुभ नामे जागे तव शुभ आशीष मांगे गाहे तव जय गाथा जन गण मंगलदायक जय हे भारत भाग्य विधाता जय हे जय हे जय हे जय 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 हे
Thank you once again, Dr. Krish. Have a great day.
Thank you.
Bye-bye, sir.
Thank you. Thank you all.
Yeah, thank you
Thank
all.
you.
Thank you.
Goodbye.
Thank you all. Bye. Thank you.
Bye-bye.
Thank you.